Okay, so we are here to talk about water potential. And water potential is basically the potential for water to leave an area. So if it has high water potential, it's more likely to leave and go somewhere else. If it has low water potential, it's less likely to leave, and oftentimes you'll see water coming that direction. So if I was a cell and I had really low water potential, like a real negative number, like negative 10 bars of water potential, you'd probably see water coming into me as that cell. So I can calculate the solute potential when given the formula. So water potential is a math problem, and it is made, we use this Greek letter psi. It is made of the solute potential plus the pressure potential. And to be honest, I don't know, maybe 1 or 2 times have I seen a problem where pressure potential was not 0. But the other 98 times I've seen it, or so, it has been 0. So 9 times out of 10, 98 times out of 100, whatever, your pressure potential is going to be 0. So unless they tell you different, assume that is 0. If that is 0, then anything plus 0 is still itself. So when pressure potential is 0, it basically goes out of the picture, and that means that your water potential is equal to your solute potential. You can't always assume that, though. You got to make sure that they don't give you a pressure potential, so you have to take that into effect. Solute potential has a formula of negative ICRT. Don't forget the negative. That's what people often forget. And I is the ionization constant. That's the number of molecules something breaks up into when it's in water. So something like salt, NaCl, splits into Na and Cl when it's in water, and so it has an ionization constant of 2. Something like glucose, when it goes into water, it stays its one little molecule of glucose, and so it has an ionization constant of 1. C is concentration. That's going to be in molarity. R is a constant, and R is 0.0831 liter bars per mole Kelvin. Okay? And then your temperature is in Kelvin. So concentration is going to be in molarity, which is moles per liter. So moles on top and moles on bottom are going to cancel. Liter on top here and liter on the bottom for concentration are going to cancel. And then your temperature is Kelvin, and so that would technically be on top, and this Kelvin's on the bottom. And so your unit is going to be bars. Okay? So let's look at an example. We have a cell, and the cell has a concentration of 0.6 sucrose solution, and the beaker, the solution in the beaker outside of the cell has a concentration of 0.4 sucrose solution, and they are 0.4 concentration, and they are at 18 degrees Celsius. Okay, so and we are assuming, because nothing is mentioned about pressure, that our pressure potential is going to be 0. All right. So our solute potential is negative. It is sucrose, which is not going to break up in water, so it's going to have an ionization constant of 1. It has a concentration of 0.4. Our R value is 0.0831, and our temperature, is going to be 291, I believe. Yes, 291. Okay, because we had to convert it, so we had to add that 273 to the 18 to get our temperature. Okay, so all we're going to do is we're going to multiply those together. So I'm going to do that really quick, 0.0831. And that gives us a solute potential of negative 9.67 bars. Okay, let's jump over to the cell. So we have the same solution inside the cell, not the same solution, the same type of solution, a sucrose solution, but it is a little bit stronger. And so we're going to do negative. It's sucrose, so it's an ionization constant of 1, concentration of 0.6, 0831, and 291, because it is also at 18 degrees Celsius. So 0.6 times 0831 times 291 is negative 14.51 bars. Okay, so it says I can calculate solute potential when given the formula. So here's the formula, and this is how you calculate it. You'll be given everything. The only thing you might have to do is you might have to convert your temperature to Kelvin. Okay, and on the formula sheet it tells you, it gives you both of these formulas. It tells you what all of these stand for, and it even tells you to add the 273 to Celsius to get Kelvin. So it reminds you to do that. The second I can statement is I can calculate water potential when given the formula. So once you know solute potential, you add it to the pressure potential to give you the overall water potential. For these, we weren't given a pressure potential, so we're assuming they're 0. So we could also say that our overall water potential is negative 9.67 bars. And the same thing over here. This is our solute potential, but pressure was 0. So our overall water potential is still negative 14.51 bars. And the third thing is I can relate water potential calculations to the direction of water movement. Water is always going to move towards the more negative water potential. So in this case, the more negative number is the negative 14. That is a lower number than negative 9. And so what we're going to see is we're going to see the water is going to move from the solution into the cell. So we're going to see it going into the cell. Some of you may have already guessed that because we talked earlier about how it always moves towards the hypertonic solution. So because these were at the same temperature, they were the same type of solution, so they had the same ionization constant. The only difference was their concentration. It makes sense that the higher the concentration, because this is a negative number, when you make this number bigger, it's going to make this number bigger or more negative. So hypertonic is oftentimes the more negative water potential unless they're at different temperatures or they're different solutions, so the ionization constants are different, or there's a pressure potential involved. So in this case, water is going to move into the cell because that cell has the lower water potential. And I hope that helps.